explain how SVM algorithm works. This video will explain the support vector machine for linearly separable binary sets. Suppose we have these two features, x1 and x2 here, and we want to classify all these elements, and we can see that we have the class square and the class circle. So the goal of the SVM is to design a hyperplane. Here we define this green line as the hyperplane that classifies all training vectors in two classes. Here we show two different hyperplanes which can classify correctly all the instances in this feature set, but the best choice will be the hyperplane that leaves the maximum margin from both classes. The margin is this distance between the hyperplane and the closest elements from this hyperplane. We have, in the case of the red hyperplane, we have this distance, so this is the margin which we represent by z1, and in the case of the green hyperplane we have the margin that we call z2. We can clearly see that the value of z2 is greater than z1, so the margin is higher in the case of the green hyperplane. So in this case the best choice will be the green hyperplane. Suppose we have this hyperplane. So this hyperplane is defined by one equation. We can state this equation as this one. We have a vector of weights plus omega 0 here, and this equation will deliver values greater than 1 for all the input vectors which belongs to class 1, in this case the circles. And also we scale this hyperplane so that it will deliver values smaller than -1 for all values which belongs to class number 2, the rectangles. We can say that this distance from the closest elements will be at least 1. The modulus is 1. And from the geometry we know that the distance between a point and a hyperplane is computed by this equation. So the total margin, which corresponds by this distance, would be computed by this equation. And the aim is that minimizing this term will maximize the separability, which we mean when we minimize this weight vector, we will have the biggest margin here that will split these two classes. To minimize this weight vector is a nonlinear optimization task, which can be solved by these conditions KKT, which use Lagrange multipliers. The main equations state that the value of omega will be the solution of this sum here. And we also have this other rule. So when we solve this equation, trying to minimize this omega vector, we will maximize the margin between the two classes, which means we will maximize the separability between the two classes. And here we show a simple example. Suppose we have these two features, x1 and x2, and we have these three values. We want to design or to find the best hyperplane that will divide these two classes. So we know that we can see clearly from this graph that the best division line will be a parallel line to the line that connects these two values here. So we can define this weight vector, which is this point minus this other point, is exactly this weight point. So we have a constant A and 2 times this constant weight A. Now we can solve this weight vector and create the hyperplane equations considering this weight vector. We must discover the values of this A here. since we have this weight vector omega here, we can substitute the values of this point, and also in using this point we can substitute these two values here. When we place the equation g using the input vector 1 times 1, we know that we have the value -1 because it belongs to the class circle. So we will have this value here. When we use the second point and we apply the function, we know that it will deliver the value 1. So we substitute here in the equation also. Well, given these two equations, we can isolate the value of omega 0 here. In the second equation, we will have omega 0 equal to 1 minus 8 times a. So, using this value, we put omega 0 in this first equation, and we will reach the value of a, which is 2 divided by 5. Now we discovered the value of a, and now we will substitute in the first equation and also discover the value of omega 0. So by dividing here, we will come to the conclusion that omega 0 is minus 11 divided by 5. And since we know that the weight vector is a and 2a, we can substitute the value of a here, and we'll deliver these values of the weight vector. So in this case, these are called the support vectors because they compose the omega value, 2 divided by 5 and 4 divided by 5. When we substitute here the values of omega 2 divided by 5 and 4 divided by 5, and also the omega 0 value, we will deliver the final equation, which defines this hyperplane, this green hyperplane, which is x1 plus 2 times x2 minus 5.5. And this hyperplane classify the elements using support vector machines. These are some references that I have used. So this is how SVM algorithm